Hello everybody, getting ready to do lesson chapter 3, review and summary of pre-calculus math today. And today we have 96 points here of classwork to do, so we got a lot of work here. And no points will go into your notebook. And teachers, here's today's bell work. Determine whether the equation or statement is true or false. Justify your answers. Students, give your students about... And this is where you put your justify your answer down here. You give your students about 5 minutes for this. Okay, welcome back for today's Bellwork Solutions. Justify your answer, e to the x minus 1. Does that equal e to the x over e? So e to the x minus 1 would be e to the x times e to the negative 1. Would be equal to e to the x over e. So this case here, these are equal expressions here. There's similar expressions, true by properties of exponents would be the reasoning there, why this equals that. And then down here, natural log x plus natural log y equals natural log xy. And that's also true by the product property of natural logs. Okay, today's lesson, we'll go right into example 1 here. Classwork 4.0 for section 3.1. Recognize and evaluate and graph exponential functions with base e. So the function of f of x equals e to the x is called the natural exponential function. And then this would be the graph of f of x equals e to the x. This is your classic parent function for exponentials here, where your y-intercept is 0, 1. And then these other points here would be on your line, your curve for f of x equals e to the x. So down here into our guided practice, we're going to use a graphing calculator. Students, get out your graphing calculators. And you're going to fill in a table here for each one of these functions. Sketch the graph of the function and identify any asymptotes of the graph. So number 16 here, f of x equals 3 minus e to the negative x. So for that one, what we have here, this would be your table for this function here. You should have these values in your table. And then you just plot either by hand, or you can go into your graphing calculator, and then we have a horizontal asymptote here, y equals 3. Then this would be your graph here, would be a curve that goes like that. And then up here at y equals 3 would be your horizontal asymptote for that. And then down here, same thing, put this into your calculator. This would be your table of values for that one. And then our horizontal asymptote would be y equals 2, which would be here. This would be our y-intercept, or rather our y, not our y-intercept, but our horizontal asymptote. And then your graph from left to right would go like so. So that would be what that graph would look like there. Into example 2 for section 3.2, sorry. Graph logarithmic functions with base a and recognize, evaluate, and graph natural logarithmic functions. So in this situation here, we have graphs of g of x equals log base a x and f of x equals a to the x are reflections of each other in the line of y equals x. So that would look like this here. Here's y equals x, and then this would be f of x equals a to the x. And this would be f of negative 1 of x, which would be the inverse, which would be g of x equals log base a to the x here. This would be the inverse of this graph here, and it indeed is a reflection in the line of y equals x. So let's go into this another situation here. The function defined by g of x equals natural log that x being greater than 0 is called a natural logarithmic function, and then that is what this is here. Again, it's a reflection of f of x equals e to the x, and it's a reflection in y equals x, that line there. Let's try one. Find a domain, vertical asymptote, and x-intercept of the logarithmic function. and sketch its graph by hand. So g of x equals the negative of log base 2x plus 5. So, okay, moving into our example here, g of x equals negative log base 2x plus 5. Using our change of base formula here, we would have 5 minus natural log x over natural log 2, natural log x over natural log 2, the negative of that. And then we're going to stick our plus 5 out in front like that. And then the table of values for that function there, once you put that into your graphing calculator, will be these values here. And then here is your domain. X will be greater than 0, so everything's over here on this side of your y-axis. Your vertical asymptote would be x equals 0, would be your vertical asymptote, meaning your y-axis would be your vertical asymptote. And then your x-intercept will be way out here at 32, 0. And then this would be the graph of that function here. So the vertical asymptote with here just goes like this, but it never crosses your y-axis, and it eventually does cross your x-axis way out here at 32, 0. Okay, moving on now into our next example, 3.3. Use properties of logarithms to evaluate, rewrite, expand, or condense logarithmic expressions. So let a be a positive number, a cannot equal 1, and be a real number, and u and v be positive real numbers. Number 1 product property would be log base a uv, would be the same thing as equals log base a u plus log a v. That'd be your product property. And then you could do the same thing with natural log as well by adding your two factors here of log. You could add them, which would be the same thing as multiplying them together. And then your quotient property would be log base a u divided by v would equal log base a u minus log base a v. And then natural log u divided by v would be natural log u minus natural log v. And then our power property, log base a u to the n, would equal, we bring our n out in front here to n log base a u. And then for natural log, do the same thing here. You bring your n out in front, and then you would have n natural log u. Let's try one now. Condense the expression to the logarithm of a single quantity. So we have 1/2 natural log 2x minus 1 minus 2 natural log x plus 1 up here for a guided practice here. Students, I want you to do this one down here before I reveal what the solution is. Try to do that on your own. But for now, to give you some modeling on how to do your independent, I do your independent first. How about that? Must be Friday. So natural log x minus 2, 5 minus natural log x plus 2 minus natural log x cubed. That's for this expression here. This would be the way that you would exponent it back up. You would bring this out up here to the 5th power, and then natural log, that stays the same. Then 3 would be natural log x cubed. And then here, we would next do our, we have a subtraction here of natural log x plus 2 times x plus 3 here. So we have this quantity here, and we are subtracting natural log x plus 2 and natural log x cubed. And then we can combine like terms here, and then we have x minus 2 to the 5th divided by x plus 2 as well as x cubed. So that'll be how we do that. And then up here, this becomes a square root. Anything to the 1/2 power will be the square root, will be radical natural log, radical 2x minus 1 minus natural log x plus 1 squared. This goes up here like that. Then we have a subtraction here, which means this is divided by this quantity here. And then we put our natural log out in front, so we have natural log radical 2x minus 1 over x plus 1 squared. Into our next example here for section 3.4. solve more complicated exponential and logarithmic equations. To solve more complicated equations, rewrite the equations so that the one-to-one properties and inverse properties of exponential and logarithmic functions can be used. So let's try one of those now. Solve the equation algebraically, round your result to 3 decimal places. So we have a little bit more complicated exponential equations here. So xe to the x plus, or rather, yes, plus e to the x equals 0. So we can factor out e to the x power here. So x plus 1 to the e to the x equals 0. Then x plus 1 equals 0, since e to the x cannot equal 0. So we can take that out. We just need to find what x plus 1 would be to make this quantity equal 0. X would have to be equal to negative 1 to make that equal to 0. And then down here, 2x e to the 2x plus e to the 2x equals 0. Again, we're going to factor out an e to the 2x. We're left with 2x plus 1 multiplied by e to the 2x equals 0. And then 2x plus 1 would equal 0 because e to the 2x cannot equal 0. And then when we factor that down, we have x equals negative 1/2 for those two. On into 3.5. Recognize the 5 most common types of models involving exponential or logarithmic functions. So exponential growth model would be y equals ae to the bx. B has got to be greater than 0 for a growth model. And then exponential decay model would be y equals ae to the negative bx. B has got to be greater than 0 here for the decay model. And then for the Gaussian model, we have y equals ae to the negative of x minus b quantity x minus b squared divided by c. That would be your Gaussian model. And then for a logistic growth model, y equals a divided by 1 plus be to the negative rx. And then for logarithmic models, we have y equals a plus b natural log x, and then y equals a plus b natural log base 10x. So this is kind of like chapter 3 in a nutshell right here. And we do this all in 3.5. So here, up here we have matched the function with its graph. So we have y equals 2e to the negative x plus 4 squared divided by 3. So which one of these would match this function here? Same thing down here, y equals 6 over 1 plus 2e to the negative 2x. So which would be a match for 125? So y equals 2e to the negative x plus 4 squared divided by 3 is a Gaussian model, which is right here at A, almost like a miniature normal curve there. So that would be your Gaussian model, used a lot in statistics. And then for 126, this would be a logistic model, which would be C right here. You have a curve that goes like this, has 2 horizontal asymptotes for the logistic model there. Okay, going on now into 3.6, use a graphing utility to find exponential and logistic models for data. So an exponential model can be used to estimate the amount of revenue collected by the Internal Revenue Service for a given year, and a logistic model can be used to estimate the percent of defoliation caused by gypsy moths. So these models, the different models can be used for different phenomena. Okay, moving into our next guided practice here. Number 133, modeling data. Each ordered pair, T and N, represents the year T and the number N in thousands of female participants in a high school athletic programs during 9 school years, with T equals 1, corresponding to 2000-2001 school year. And then here's your data points here, 2000, 2000, 2001, 2001, 2002, 2003, 2004, etc. So with this data set here, you need to enter this into your graphing calculator and then use the regression feature of a graphing calculator to find a linear model, an exponential model, and a power model for the data, and identify the coefficient of determination for each model. So by entering this into your list, and making a table for each type of function here, your linear. Let's start with the linear. And for the linear model, when you enter it in, this is your equation here that you'll get that matches up to this data set here. It would be n equals 41.5t plus 2722. And then your coefficient of determination, which is right here, coefficient of determination will be 0.9785 for the linear model. And then for this would be a graph here of your linear model. It looks, just by looking at it, looks like a pretty good match. But let's continue with our other models here. Exponential model. This will be our equation here once you enter it, and then use your regression to find the equation of the exponential model. For that data set, you have 2728 times 1.0142 to the t power, and then your coefficient of determination would be 0.9818. That's better than the linear because of the 9.8 is closer to 1 than the 9.7. And then for the power model, we have 2727.6 t to the 0.0497 would be our power model. And here is our coefficient of determination here is 0.8398, not so great. So it looks to me like the exponential model. Okay, so finding out now about our exponential and our power models further, the graphs of our two models here is here's your exponential here. That looks pretty good. And then here's our power model here, not so good. I mean, this is the data plot of that, the dot plot of it. And then here is your curve from the power model regression. And then here's our exponential regression here. C, determine which model fits the data best. The exponential model, this model here, with r squared equals 0.9818 is the best fit because the coefficient of determination is closest to 1. This is the closest one here to 1. And then D, use the model. Use the model we got for our exponential model. Use that model to predict the number of participants during the 2009 and through 2010 school year. So that'd be year 10. So we put that, that's where our T was there. And then when we crank that out, we have 3.141.09 or 3.141, 3,141,090 female athletes on our year 10, adding up all of our years together. That'd be up here, 3.141, which would be right there. And then E, use the model you chose in part C to predict the school year in which about 3.7 million girls will participate. So to find that year, we solve for T here, 3720 equals 2728 times 1.0142 to the T power. Then we solve for T here by using our natural log, both sides. This goes out here, and then T would equal natural log 1.36, repeating over natural log 1.0142. And that comes out to 22. So the school year of 2021-2022 would have 3.7 million girls participating. Hooray! And that is our lesson for today of pre-calculus math. Email me here for note-taking guides or solution PowerPoints or questions. Thank you.